Welcome to one of my favorite units that we teach. It's a short, quick, easy unit. Matter of fact, we're going to be testing over it next Friday because it's short and sweet, but it's all about the periodic table. We're going to talk about how it's arranged, why it's arranged, and the way it's arranged. There are certain properties that appear at regular intervals. So it is one of my favorite units because it's really cool how everything works together. So let's get going. So today's lesson is just about the periodic table. The next lesson will be about the trends and how we can kind of predict some of their properties. But why is what is the importance of the periodic table to us? First of all, you get to use it on every test. Okay, it is one of the most useful tools to a chemist or to a high school chemistry student, and it organizes a lot of the information about the known elements. Before we had the periodic table, it was a huge mess. Okay, we had elements that we knew, they weren't arranged they weren't arranged at all. People had to kind of guess at what the properties were. It's like going to the grocery store and there's like 10 different cereals on 10 different aisles, and you got to walk all over the place. So it was a way to organize that chaoticness of the elements known at the time. It was also difficult for people to find information, and it just didn't make sense. Like, it was random. So the father of the periodic table is Dmitri Mendeleev, and there's actually a element named after him, element 101, which is Mendelevium. They gave him that honor. Obviously, by the time that was created, because it's man-made, he was long gone. And this is how he discovered this pattern. So he decided to put the elements in rows by their increasing atomic weight or atomic mass. You could put mass there instead if you would like, because nowadays we say mass, not weight. He put the elements in columns by the way that they reacted. So he noticed that there were some similar properties, and so he put them in order and by columns and rows. But there were some problems. For instance, there were some discrepancies in the atomic weights, and then of course there were some at that time. Not all the elements had been discovered, and so he left spaces in the periodic table that he was writing for undiscovered elements that he said would be in those particular columns. In other words, he said, hey, we don't know what this element is yet, but we're going to discover it, and it's going to have properties X, Y, and Z, and turns out he was right about many of them, which is kind of cool. Your notes say that he published that first periodic table in 1869, which was a long time ago, 100 years before I was born. And we already talked about that. So the current periodic table now, in 1911, Henry Moseley discovered a new pattern, and this was after the discovery of the nucleus, and this is after we decided that we needed to identify elements by their atomic number instead of their atomic mass. We no longer do atomic mass. We identify things by its atomic number. And he discovered a new pattern based on that, which is the current way that the periodic table is arranged. It is by the order of increasing atomic number. It's the same periodic table we use today, the same order. It does look slightly different than 1911 because new things have been discovered. For instance, in 1911, when he wrote that first table based on atomic number, the noble gases weren't known because, quite frankly, they're not reactive. So how would they have known about them? So they discovered them later after this first table, and they added that last group on there. So this means, and this is the title of the unit, and this is also, since it's a law, you better know it, and it says that the periodic law states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. In other words, they appear at regular intervals periodically based on their atomic numbers. And I want you to think in your mind and guess why that is the case, why those properties are appearing at regular intervals. So the arrangement of the elements in order of their atomic numbers, they arrange it so that their properties fall in the same column or group. Remember, the column is up and down. And the reason that they do this, we'll talk about in a second. We call the rows of the periodic table, horizontal, side to side, are called periods, and they're 1 through 7. We've talked about how in your lifetime you'll probably see a row 8 added whenever they come up with the element 119 that they're working on now. The vertical columns are called groups, or sometimes they're called families, and they're 1 through 18. Okay? Sometimes on tests, kids get those backwards, and I tell you, remember it this way. You have 7 periods in a day, just like the periodic table does. Periodicity is another definition you're going to be responsible for, and it's the similarities of the elements in the same group is explained by the electron configuration around the nucleus. So and we already know this from our electron configuration unit, but everything in the same group has a similar electron configuration, meaning their outer electron configuration is the same, it's just in a higher energy level. So in other words, potassium ends in 4s1, sodium ends in 3s1, lithium 2s1. They all are ending in s1, and it's that one electron in the outer shell that gives them a similar property. So what about the groups of the periodic table? We're going to talk about, some of them have names, and they have specific properties, and so we're going to talk about that. Remember, the elements in the same group have the same similar and chemical properties. The reason for is that they have the same number of valence electrons and they will form the same kind of ions. But really, number 2 depends on number 1. So really, the main reason is that they have the same number of valence electrons. So they behave very similarly. So groups or families on the periodic table, they are the vertical up and down columns, and they are grouped into families. So most of the time we're going to talk about families being one column, but there are several columns put together. For instance, 3 through 12 we're going to call the transition metals, and they are going to be grouped lump sum together. Okay. Some families have names rather than numbers, just like your family has a common last name. So hydrogen is its own entity up there by itself. Okay. It is not part of group 1 in that it doesn't have similar properties. So it's its own family. Remember, hydrogen is diatomic, reactive gas. Remember, diatomic means when it's by itself, it appears as a H2. Let's write that where you can see it better, H2, because it's bonds to itself. Fun fact, the Hindenburg, which y'all are way too young, I'm even too young to remember it, but it was the first blimp and it blew up, and it was because of hydrogen is so reactive. Hydrogen is also a promising alternate fuel source by combusting hydrogen and oxygen as a fuel source, and the byproduct is water, which is much safer than the byproducts of the gasoline and stuff. But it is, unfortunately, very explosive, so they're still trying to work it out where it's safer. So the first group that we're going to talk about is the alkali metals. Okay, it's the first column, lithium all the way down through francium. Remember, it does not include hydrogen. They are very reactive metals, and by very reactive metals, we're going to say they are the most reactive. They are the most reactive of the metals, and they are always combined with something else in nature. They are never found free in nature by themselves. They're very soft. They're soft enough to actually cut with a butter knife, and of course, they have that NS1 configuration. When I say that they're very reactive, and the reason they're never found in nature is they're very reactive with water and air. And so because of that, they're never really found by themselves. We can isolate them. We usually store them under kerosene, gasoline, or mineral oil to keep them from being reactive. But they are the most reactive of the metals. And they tend to form a +1 ion because of that one valence electron in the NS1. So what it likes to do in order to get that octet we talked about, it likes to kick out that one electron, and then it has an octet underneath. The next group is the alkaline earth metals. They are also reactive. They're also very reactive. They are less reactive than group 1, but then they're like the next most reactive. That is the second column. They are always combined in nature too. Several of these are important minerals that we need for our body, such as calcium and magnesium. And of course, they end in that NS2 configuration, which if you are doing the prediction correctly, they're going to form a 2+ ion, is what they'll do, because they'll like to give away 2 electrons. The transition metals are the next group we're going to talk about, and those are in the D block. Okay, it's groups 3 through 12. They have your classic metallic properties that you're used to thinking of when you think metals. I'm sure when I said that the sodium and group 1 metals were soft enough to cut with a knife, you're like, how can it be a metal? But it is. But the classic metal properties are the ones we think about, like conductivity and shiny, also called luster, that sort of thing. They are less reactive than your group 1 metals and your group 2 metals, but a lot of them include your jewelry metals, such as gold and silver and platinum. And they're the ones that we would use as when we think of metals. For instance, iron is in there, and that would be used in construction. Okay. The classic metallic properties that we are referring to are things like malleability, which means hammer into a thin sheet. Ductility means you can pull it in a wire, so a lot of our wiring, especially copper, is pulled into that thin wire so that it can conduct the electric current along the wire. Luster means shiny, and then they're good conductors of both heat and electricity. So let's write that down, good conductors of heat and electricity. Group 13 is our P block elements. That starts our P block. Group 13 through 18 are our P block elements. We've already talked about that. The thing about group, oh, that got left off. That should say group 13 through 18, shouldn't it? Yeah, that got left off. Sorry about that, guys and gals. 13 through 18, but that's already on your notes. They are our P block groups. Okay, and they contain metal, non-metals, and metalloids. Okay, metalloids are something that basically have the properties of both metals and non-metals, and they are good semiconductors. And semiconductors are what we use in our electronics. In your phone, a lot of silicon is used, which is right here, and this is a zigzag line along the periodic table. And if it touches that zigzag line along here, all of these, with the exception of aluminum, then they are considered to be a metalloid. On the big periodic table and in the classroom, that line is not there, but I believe it is on your periodic table that you use in class. Okay? So you need to know that metalloids are semiconductors, and there's only 1, 2, 3, 4, 5, 6 of them. Now, within the P block, we've got some that we talk about a little bit, and some places will call them by the top element in the group, and they just call them that, the boron family. But it's different in that their properties aren't as predictable, because you've got, like for instance, you know, in the carbon group, you can go from carbon, which is a non-metal, then you got some metalloids, and down at the bottom you got metals. So the predictability is not quite as predictable, I guess is the word to say it. But part of that is because once the d orbital becomes available to them, as you go down those groups, then they behave a little bit differently. Okay, so elements in group 13, boron is kind of important, but aluminum is the one we're going to really talk about in there. Aluminum was once thought to be very rare and expensive, and now we use it as a disposable metal. You know, aluminum foil, aluminum cans, that sort of thing. We don't really have a shortage of that. The carbon family, carbon is in element group 14, and of group 14, carbon is going to be the most important one because all life contains carbon. It's also in computers, and carbon is the basis for an entire branch of chemistry. It's called organic chemistry. You don't need to know that. I'm just going to give you a little FYI. If you're going to go on to be a doctor or anything in the medical field or vet or whatever, you're going to have to take organic chemistry. And it is known as a weed out course. I didn't think it was that bad, but a lot of people hated it. Silicon and germanium are also important semiconductors in that group. We already talked about silicon being in your phones and your chips. And you've heard of Silicon Valley in California, and that's kind of where it gets that name, because that's where a lot of the electronics are not just made, but like that's where the latest iPhone research is going on, et cetera, et cetera. The nitrogen family, group 15, is nitrogen makes up over 3/4 of our atmosphere. So basically, it's all around you right now. Nitrogen and phosphorus are also important in living things. If any of you do any kind of gardening or yard work, the fertilizers always have a nitrogen-phosphorus ratio in them, because those are important to plants especially. And most of the world's nitrogen is actually not available to living things. So the plants can't utilize the nitrogen in the air. It has to go through a chemical process in the soil to be able to uptake it through its root. Okay? And then whenever you've struck a match, the stuff on the end, that red tip, is going to be phosphorus. The oxygen family, or sometimes they're called the chalcogens. Of course, obviously, oxygen is important to life because we breathe it. It's half the ingredients in water, so it's very important. And then many things that you think smell bad, it's sulfur is what you're smelling. That smell of rotten eggs is coming from sulfur. And so it's not very pleasant to our senses. The halogens, very important group. These are it says very active, and I'm going to tell you that these are the most reactive of the nonmetals. Most reactive nonmetals. They are also diatomic, so they're diatomic. We need to write that down. Remember, that means, So we have fluorine, we have bromine, I left out chlorine in the middle, iodine, and astatine is in there, but there's so little of it we don't ever deal with it, okay? Again, just like group 1 metals, and they're never found free in nature, and so guess what they like to bond with? They need one electron, and the sodium and potassium and all that in group 1 want to get rid of one electron, so that's how we get a lot of our compounds. They will form a -1 ion. Okay? They will form a -1 ion. And that brings us to the noble gases, the last group on the periodic table, group 18. They are unreactive monoatomic gases. Okay, helium is a noble gas. Okay, let's talk about that for a second. Helium is up here by itself, and it ends in 1s2, and that's because it has 2 electrons in its outer shell, so it is a complete outer shell. The rest of the halogens end in the ns2, ns6, which gives them 8, which is an octet. That's why they are so unreactive, because they've got a full outer shell, and so they're very, very stable, okay, because they have that full valence shell, okay? And then lastly, we have the lanthanides and actinides down at the bottom. Of course, we know those as the F blocks, also the ones that we get confused on for doing electron configuration. The good news is we don't talk about them a lot from here on out because they're just not that reactive. The only one that you would ever have actually heard of on a regular basis, of course, is uranium, because that's what's used in nuclear reactors. But they are part of the F block. They are considered, actually we usually sometimes call them inner transition metals. And the reason being is because they fit into the transition metals. So sometimes we refer to them as the inner transition metals. And of course, these are in period 6. And then these are in period 7. Excuse me. And so basically you need to know that the lanthanides are shiny reactive metals. Those are still naturally occurring. The actinides are unstable and radioactive, so they're almost all of them are radioactive, and of course they're filling the 5f orbital. And that's where we're going to stop. We'll pick up with periodic trends tomorrow.